just model, okay, this type of thing. So basically, I mean, this is sigma t squared, right? So, and that's basically called exponential smoothing. I will explain this later in the exercises. Okay, so what do I mean by that? Okay, now this is just summarizing these two properties, and then we're gonna go further. Okay, but I think you've probably seen this somewhere. Okay, I mean, this is the integrated conditional, integrated generalized autoregressive conditional heteroscedasticity model. Allows us basically to model the variance here of the process by using the exponential smoothing here. Okay, that's basically important for estimation. So if you look at, for instance, historical volatilities, you would how would you estimate historical volatilities? I mean, the thing is this, you know, the observation in the past or basically have a large time lag are not so important than observations here, for instance, the current observations. Okay, because basically the volatility or the variance of the process is time dependent. So for estimation, you would assign different weights to observations which have, you know, time lags that are relatively large, because these observations are not important or not that important, and that's what you could do with using the exponential smoothing technique. Okay, now we will also examine certain characteristics of integrated processes again in the next chapter, so we don't use this now. Okay, so that's the first process, okay, that we're looking at. The second one will be the so-called gauge in mean process. Okay, so this is going to be the second one, so you can say also gauge M, okay, gauge M, or you can say gauge in mean. Okay, so that's how it's spoken in mean. Okay, so this is going to be the second extension here, and it's going to be as follows. Okay, so the gauge in mean process looks like this. So here yt, and here you have, let's say, I mean, let's start with xt first. Okay, xt is basically a gauge model. So let me just add here this to it. So xt is a gauge model. So if there was nothing left here, then you would get a gauge model. So that's just the corresponding version here for that. But you would also have, and this is what gauge in mean means, okay, so you'll also add a different expression here, and I'm calling this theta times sigma t, okay, and that allows us actually, okay, certain properties that, you know, general gauge processes don't have. So this is just an extension here for that. Okay. All right. Now, what does it mean basically? All right. So gauge in mean process, it adds a heteroscedastic term into the mean equation, resulting in higher returns. Okay. So when you have this is the, okay. So this is what you have, a heteroscedastic term here. Okay, so this is what we add here. Okay, so basically time varying variance. Okay, so this is what it means, and this allows us to model basically higher. I mean, the empirical evidence suggests, I mean, especially specifically for stocks, is that if the volatility is large, okay, then returns tend to be high as well. Okay, so basically this is this is what empirical evidence suggests. Okay, so when basically volatility is large, then returns tend to be large as well, and that's why we also add this heteroscedastic term here for the mean of the process. Okay, so that will have an impact here of the mean of the process. Again, so if the volatility is large, okay, let's say, then also returns of the process tend to be large as well. Okay, so this is what empirical evidence suggests. Okay, so higher returns, okay, returns, okay, so the empirical evidence is what has, so returns on stocks, for instance, or asset returns tend to be high, okay, when the volatility is large, okay. That's why it was introduced here. Okay, so large volatility means that volatility is, of course, a standard deviation of the asset returns. Okay, so when the standard deviation of the asset returns is large, then also the returns tend to be large as well. This goes hand in hand. I mean, not always, but sometimes it does. Okay, so that's why it was here. This heteroscedastic term was added here to it, and that's why it's called basically the Gaussian mean process. Okay. Now the Gaussian mean process has also a different property, namely the following. So when you look at the autocorrelation of the process, and the autocorrelation of the process will be as follows. So here your yt and here your yt plus h. So I'm going to look at that. So this is going to be equal to the autocovariance of theta times sigma on the one hand, and then you'll hear in this case, okay, you have theta times sigma t plus h, all right? And of course, you can omit the autoregressive, I mean the gauge part, because the generalized autoregressive conditional heteroscedastic part is not autocorrelated, as we have seen this before. Okay, so this is not autocorrelated. Otherwise, it would not be stationary. Okay, remember that. I mean, the autocorrelation is not there. So you could basically neglect this, and you will have that this is going to be equal to theta squared times the autocovariance of the volatility process. Okay, so this is the second property that processes has. So if the gauge M process is no longer serially uncorrelated, if the parameter theta is equal to 0. Okay, so that's the second part. Okay, autocorrelation basically, okay, so this allows us basically certain property that the process has. Okay, so the autocorrelation of the process depends on theta. Again, the gauge part is not autocorrelated. Maybe remember that. So the autocovariance of the process will be equal to 0, but here this is not the case. Okay, so basically gauge M, okay, gauge M or Gaussian mean process is no longer serially uncorrelated. If, I mean, provided that the parameter is not equal to 0, okay? So provided that the parameter theta is not equal to 0, okay? So that's the second property that this process has. And, well, I mean, this is, you would also get, okay? Again, returns tend to be high when the volatility is large. This is whatever empirical evidence suggests. And basically, that's, you know, the process allows us actually to include autocorrelation here for the process itself, which is not the case for the generalized autoregressive conditional heteroscedasticity model. Okay? Now, and the third one that I'm going to introduce here is the E-gauge model. Okay, and then we're going to discuss them one by one. So E-gauge is basically the exponential generalized autoregressive conditional heteroscedasticity process. Okay, so this is the exponential generalized autoregressive conditional heteroscedasticity. Okay, so basically it allows us, I mean, to to model the sign and the magnitude of the noise to have separate effects, okay? So, I mean, the sign, okay, so allows, okay, so this is what we'll see later. So this allows the sign, and the magnitude of the noise to have separate effects on volatility. Okay. On volatility. Okay. Now how, and this is what you need to consider. Okay. Now this is called an Egorge process. Okay. So basically you will have that y is said to be an Egorge, so an exponentially generalized, okay, blah 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 blah. Okay, so I just simply call it Egorge process, okay, of order p and q. Okay, if the following representation is accurate, so let's say if you have the following, that yt is equal to sigma t times epsilon t, and here you have not t, basically not sigma squared, but the logarithm of sigma squared. Okay, I mean basically you can use any function or any transformation here of the process itself, and it's used by logarithm because we're not just looking at price changes but also the changes here in the volatility again. So this is just a different concept here, but you can use any function you like. It doesn't matter. I mean, depending on the process, whether or not it makes sense. Okay, so what I'm using here is that the following. So basically you have the logarithms. Okay, so I mean the first one, and here you have a constant. Okay, let's just start with a constant. Okay, so I call this constant, let's say v. Okay, and you have the betas. Okay, so beta 1 times ln of sigma t minus 1 squared. Okay, that's the first one, and then plus etc etc etc, and the last one will be ln of sigma t minus q squared, p squared here for that. Okay, so that was just the volatility part. And for the noise, you have something else. Okay, so because yes.
There's no beta anymore?
Yes, there is a beta. I forgot. I just forgot. So beta p, sorry. So here you have beta p times the logarithm, and then you will have the noises. Okay, and I will just summarize that here. So you have the sum. Okay, so j is equal to 1 and q. And here you have the following expression. So here you have alpha j times the absolute value of the noise. Okay, so that's going to be the first one. And then plus gamma j, okay, times the noise itself. Okay, so in both cases you have the noise. Okay, but if let's say the noise is negative, okay, then it will have a different impact on the process as if the noise was positive. I'm not sure whether or not you see this. Okay, so basically you split, you know, the noise, and you have the two parameters. So what you do is, okay, so you distinguish between two cases whether or not the noise is negative or positive. Okay, so that's what you would do. Okay, so again, because I mean the reason for that is being that the volatility tends to be, okay, responding. I mean it depends on whether or not this increases or decreases or whatever. Okay, and it uses of course a logarithm, because if you take the exponential of that, then basically the volatility is always positive. So this is just basically the change in volatility, let's say, what you would do. Okay, because if you use the difference of the logarithms, then you could basically model the changes in volatility. Okay, all right. So either whether or not the volatility increases or decreases, let's say. and you distinguish between the two cases. Let me just illustrate this, so how it works, because that's what you'll find. I mean, you have two cases again. If, let's say, okay, so let me just illustrate this. Okay, so here is an example. You have two cases, so let's see what happens. Okay, so let's say the noise, okay, is greater than 0. Okay, so if the noise is greater than 0, then what happens here is going to be, I mean, just look at this case, is that this expression will become, okay, so alpha j times the absolute value of the noise plus gamma, okay, is going to be equal to the following. Now, if, of course, the absolute value of the noise is greater than 0, all right, no, sorry, if the noise is greater than 0, then the absolute value doesn't change, so the absolute value is going to be equal to that noise itself. So what you will have is that you have alpha j plus gamma j times the noise. That's quite obvious, okay? So again, if the noise is greater than 0, then its absolute value is also greater than 0, so the absolute value is going to be equal to the noise itself, okay? So that's quite obvious, okay? So here you have a different impact. Let's say this is the impact here, okay? So here are these parameters. This is the impact here of the noise. And if the noise itself, if, let's say, is negative, okay, so if the noise, let's say, epsilon t minus j is negative, then you will have that basically that this impact or this impulse, let's say, will have a different impact, okay, depending on the parameters. Okay, so again, so here you have gamma j times epsilon t minus j, and of course, if the noise is less than 0, then its absolute value is going to be the negative here of that. So basically, this is, I mean, you would have, or you could rewrite this as follows. So you would also do you could also do the following. So you could change that to, I use that notation, so you say yj plus, okay, so here I'd keep the absolute value, okay, so I keep this, and I'm going to change that as follows. So here minus gamma j times the absolute value here of the noise. Okay, so in this case, and then you will have that this is going to be equal to alpha j minus gamma j times the absolute value of the noise. Okay, so again, I'm using that for comparison. Okay, yes, yeah. That was a question. I thought that it was about to ask something.
Actually, yeah. Now that you're saying this, the second line. Where
This one?
plus not.
This one?
Yeah. I'm sorry.
No. What's your question? I don't understand the question.
I don't know how to call the letter yet. That's why. So it's equal to.
This one, epsilon?
No.
Gamma?
No. Yes.
Alpha?
Okay, so alpha j plus.
Times?
Times or plus?
Yes, so I know times. Yes, times. Sorry. Yeah,
So,
I screwed it up. Sorry. I was sorry about this. Times, yes. Obviously. Okay. I was looking at the same expression here. Okay. So I'm using that for comparison, guys. Okay. So here, of course, you have a different impact here. That's going to be something else. Okay. Right. So this is just a different kind of situation that you have here. Okay. So then you can compare basically these two cases. That's why I was doing it here. So that's going to be the first one. Okay. This is the first one, and that's going to be the second case. Okay. And then of course you have a different impulse obviously. All right, so you can distinguish, right? So in that case, accordance with the leverage effect, negative innovations tend to have a stronger impact on volatility. Okay, so negative innovations. Okay, so let's say, if, okay, so if these gammas are less than 0, okay, so if this is negative, okay, gamma here, then basically you would have that this expression here, this one, is greater than the previous one. Okay, all right, so then basically you will have that okay, the orange one, okay, is greater than the green one. Okay, so that's how you would recognize it. Okay, now what's the point here in this? So in this case, if gamma is less than 0, then you would find basically that in that case, in accordance with the effect that we're talking about here, is that negative innovations, okay, so, or negative impulses on volatility, let's say, tend to have a stronger impact on volatility. Yes.
Is alpha bigger than gamma? Or can it be?
I mean, it doesn't matter. No, it's. I mean, alpha is it's basically positive. Okay, so it is bigger, but I'm talking about this one here. So this expression here, the orange one, is greater than this one if gamma is negative. Okay, so if gamma is negative, okay, it's not depending on alpha. So no matter what it is, if gamma is negative, then the orange expression is greater than the green one. Okay, and what are the consequences? This means that negative innovations of the noise tend to have a stronger impact on volatility than positive ones. You understand? Okay, so negative innovations, okay, tend to have a greater or stronger impact on volatility. Okay. And this is what basically, I mean, negative returns on asset tend to result in higher volatilities. Okay. And this is what it is about. So, and this is called, this is relates to the so-called leverage effect. Okay, leverage effect, meaning that basically that this is an empirical evidence. Okay, that negative returns on assets tend to result in higher volatilities. Okay, so negative returns. Okay, negative returns tend to result in higher volatilities. Okay, so basically you would look at these parameters. Okay, so you look at these gammas. Okay, and what you would do is you test whether or not the parameter is less than 0. And if the parameter is less than 0, then this means that there is a leverage effect in the data, which means that, I mean, as you can see this here, I'm sorry, you don't see that properly, right? Why didn't you tell me anything? Okay, you should have told me this. Okay, so this means that basically negative returns tend to result in higher volatilities. Okay, so the higher, so the less the returns are, okay, or negative returns are basically, okay, so if let's say the firm is about to go bankrupt, let's say, right, I mean negative returns or whatever, okay, so then the volatilities tend to be high, so the returns tend to have high standard deviations, okay, because everybody is, you know, like kind of nervous, okay. If, let's say, the firm is close to bankruptcy, everybody's nervous, okay, you don't know what to do. So this is what empirical evidence means. And this can be modeled by this parameter gamma. So what we're doing here is that, I mean, if you want to examine whether or not there is a leverage effect or not, okay, so whether or not there is a leverage effect, then basically you would test this parameter for negativity. Okay, so basically the assumption is that can we assume that basically that the parameter is negative, yes or no? Okay, and if that's the case, or if the parameter, let's say, is significant and negative, then we would argue that basically that from the empirical perspective that there is a leverage effect in the data, meaning that higher returns, or sorry, negative returns tend to result in extremely high volatilities because the impulse is different. Okay, so the response here is basically different. Okay, so that's how you would examine this negative effect, and this is what is able to be captured by this exponential Gorge model. Okay, so if, let's say, the parameter, okay, is negative, then we would argue that there is a leverage effect in the data. Okay, that's basically how you would examine this issue here. Okay, so we will look at examples next time. I think I'm not going to start here now. So we'll look at the exercises later on, and then we'll see whether or not, you know, for instance, there is a leverage effect in the data whatsoever. Okay, so then you're going to see an example. I have uploaded basically some exercises too here to this chapter. Maybe you can check it out, and we'll have a look at that later on. So, I mean, this is the particular question. Okay, so there was a result in the data, variances whatsoever, and the question is there a leverage check of the returns from the empirical point of view. Okay, so this is basically exercise 6.4, but we'll look at that I think tomorrow. So I just 5 minutes less, but I don't want to start here with that. Okay, all right. So that's how it works. So basically, we look whether or not the corresponding parameter that is estimated is negative or not, and we test this. And if it's negative and significant, then of course we would argue that there is a leverage effect in returns. Okay, so from the empirical perspective. So that's just something that you would have from the practical point of view. All right. There are in EFUs, for instance, the Gorge M model. Okay, or the eGorge models are, and all these models are implemented already. Okay, and of course, before we do this, we'll see, I mean, how estimation works. Okay, so how it's estimated, because in this case, we assume that the noise will be normal. Okay, so we'll assume that the noise will follow the normal distribution. If the noise will follow the normal distribution, then of course we will get the estimation by the likelihood method. You probably remember what the likelihood estimation is, so maximizing the so-called likelihood function with respect to the parameter, because in that case you would be able to develop a density here of the process. Okay, so you would get the density of the process. Okay, so this will be a semi-normal density, of course, if you assume that the noises are normal, let's say. Okay, why normal? Because it's easier. Okay, that's the only thing that we do. Okay, so why would we assume something else? The noises are normal, so if the noises are normal, then you would get basically a function which depends on the normal distribution. So then you would get the corresponding density, which is maximized with respect to the parameters, and that's how you would estimate the corresponding Arch and Gorge models. Okay, so in this case, we need that assumption because otherwise we would not be able to estimate the corresponding parameters, okay, unless we would have a distribution assumption here for the noise. Okay, so this is how it works. But we're going to talk about it tomorrow. Okay, so tomorrow we're going to talk about that issue. Okay, and then we'll, of course, we'll look at some exercises as well. Okay. So that was it. Okay, so basically you would have that, whether or not you would have Arch and Gorge effects, is that you would look at the squares of the process, and then you would estimate an autoregressive process based on the squares of the observation. and then you would examine whether or not the process has arch or gauge effects. Okay, so this is how it works. Okay, now we stop here and then we continue next time, and then we're also going to start with chapter number 7, which will be about integrated processes. Okay, all right, any questions? No questions? Okay, if you can ask me.